Hi everyone, welcome to AWM Pitt Grad Seminar. Thank you for joining today. Today we have two speakers. One is Shiyue Li and another is Sining Gong. Both are PhD students from Brown University. So our first talk will be on equivariant log concavity of independent sequences of claw-free graphs by Shiyue Li. And our second talk will be convergence of Lagrange FEM of Maxwell eigenvalue problem in 3D. That will be given by Sining Gong. So first speaker, Shiyue Li, you can go ahead.
Okay, so thanks for the invitation. So I'll tell you a little bit about sort of a rather new research direction in math or in combinatorics. That's equivariant log-concavity. So I'll first tell you some definitions, and we'll discuss what are some strengths of this definition compared to some familiar notions of log-concavity that you may or may not know. And then I'll show you some examples. And the example that I mentioned in the title / the abstract will be the main example here. So let's recall what is log concavity. So it is a rather natural and ubiquitous notion in combinatorics. So usually we say that a sequence A1, A2, A3 of real numbers is log concave if you look at every item in your sequence AI and you square that, and that's greater or equal to the product of its neighbors, I minus 1 times I plus 1, we say that this sequence is log concave. So here are some examples. So the most familiar combinatorial sequence, binomial coefficients, is actually log concave. If you feel like fix an n and then you compute n choose 0, n choose 1, n choose 2, and this forms a log concave sequence. And you can compute this using, say, your favorite formula, n factorial divided by n minus k factorial divided by k factorial, something like that. Or you can use your favorite combinatorial trick to check that this actually holds. So the second example also arises from combinatorics. So it's called the Stirling numbers of this first kind. So I denote it as little as nk. And for each n, it counts the number of permutations inside the symmetric group Sn that has k cycles. So what this means is, let me demonstrate using an example. So suppose your n is 4, and here if I look at the case when k is equal to 1, what this means is I want to look at the cycle, a permutation that permutes 4 elements that has exactly 1 cycle. So I can do this by, suppose I arbitrarily start with 1, and now I need to decide where 1 wants to be sent to. So there are 3 different ways I can choose. So I can choose 1 to be sent to 2, 1 can be sent to 3, 1 can be sent to 4, right? And so if you sit down for a second and you realize the number of permutations with exactly 1 cycle is exactly the same as the number of permutations on 2, 3, 4, because you are fixing 1 and then you're permuting the order of the set 2, 3, 1. So we all know that when you count the number of permutations on this set 2, 3, 4, which has cardinality 3, this gives you 6 elements. So you do the similar thing and you count the number of permutations in S4 with exactly 2 cycles. So what you do here is you list look at these 4 elements, and then you think about, oh, how can I form 2 cycles? So you can say let 1 be sent to 4 and then 2 be sent to 3, and just like form 2 loops. So this is one type of loop, and you sit down and count how many there are, and you realize there are 3 kinds of this kind of loop. And there's another type of loop that's given by a choice of a fixed element. So say if I choose 2, and then I let say the rest of the 3 elements go to each other in a cycle. So I can sit down and just like play this game, and if you spend 5 minutes and you realize there are 8 different kinds. So there are 3 kinds of this and then 8 kinds of this. So in total there should be 11. So basically you just do this kind of counting for every single n, and this sequence for n equals to 4, I have put here. You can check that this is also log-concave. So if you multiply 11 with itself, you get 121, and then that's greater than 6 times 6, which is 36, for example. Okay, so this sequence is also log-concave, and it's very well known to be log-concave. So there are proofs for this. And then a very closely related log-concave sequence is something called Stirling numbers of the second kind. So it counts the number of, so fixing an n, and big S k, n comma k, counts the number of partitions of the set 1 through n with k non-empty parts. So here I have drawn for you the case when n is equal to 4. So on top, this is saying let's partition the set 1 through 4 into just one non-empty set. So the coloring, this red coloring means everything is in one part. So there is exactly just one such partition. Okay, and then the second level counts the number of partitions of 1 through 4 into exactly 2 parts. So the coloring, this green coloring is saying that's one part and this is one part. And or you can partition it into 2 parts like this. So this picture tells you that there are 7 such partitions. And so you do the same for 3, partitioning into 3 parts and partitioning into 4 parts. You count the number, you get 6 and 1. And to check that this sequence is also log-concave when n is equal to 4, you just square 7, you get 49, and that's greater or equal to 1 times 6. And then you check for every index. And there is also a combinatorial way of proving this. So this one really fun proof that I really like is in this book that talks about generating functions. So, okay, another related but like example of a different flavor is called graph matchings. Or graph matching numbers. So given a finite graph, here I mean graphs that do not have weights on their vertices and do not have loops, like an edge connecting one single vertex, and do not have parallel edges like this. So finite simple graph. So I can look at the set of, for each k, I can look at the set that consists of matchings in this graph that has exactly k edges. So here is one example I can draw. So suppose I have this 6-cycle graph, and suppose I let k to be 3, then one such matching on graph, on the 6-cycle graph, that has 3 edges is this one, for example. Okay, so a matching means a set of edges that do not touch each other, do not share common vertices. So this sequence, once you fix your graph and you look at the cardinality of the sets mk indexed by k, This sequence is also log-concave, and it's a famous result in 1972. And the proof, I can say a little bit about the proof. So the proof is given by the following. So Newton in 1707 somehow decided to study something called real-rooted polynomials. So he proved that if a function is real-rooted, then the coefficients of f is log-concave with no internal zeros. So that means if you have two items that are non-zero, then they cannot sandwich a number that's zero. So the content of this 1972 proof is that the polynomial, the generating polynomial of this graph matching number is real-rooted. So that implies that this sequence is log-concave. And then in 1996, Grafenholler gave an injective combinatorial proof of the log-concavity. Namely, he constructed a set map from the Cartesian product of the set consisting of matchings with I-1 edges paired with the set of matchings with I+1 matching edges into the Cartesian, the pairs of matchings of size I and matchings of size I. So this, once you can establish such an injection, this automatically implies log-concavity on the cardinality. Okay, so one last example is that this thing called independent sequence of claw-free graphs. So a graph is claw-free if no induced subgraphs of G is this thing called bipartite graph K3, 1. So it looks like this. So you have three vertices here, one vertices here, and they're fully connected, but you cannot let these three vertices to be connected. So it looks like a claw. Okay, so a vertex set in this, the vertex set of G is independent if any pair of vertices is non-adjacent. So for example, here, if I look at this complicated graph, and then I look at the set of blue dots, blue vertices here, none of them are adjacent to each other. So that's an independent set of cardinality 1, 2, 3, 4, 5, 6, 7, 8, 9. So it turned out the sequence, if you look at the sequence of independent sets of size K on G, and you count their cardinalities, and that is also a log-concave sequence if your graph is log-concave. So someone proved this using combinatorial methods in the 90s, and then turned out in 1906, there's a new proof using the real-rooted polynomial method, that if you have a claw-free graph and you look at its generating polynomial, whose coefficients are the cardinalities of the independent sets of size K, and this polynomial is real-rooted. So this was proven by Shednovsky and Seymour in 2006. Okay, so I've been talking for like 10 minutes more, but so far we haven't talked about equivariantness. Everything here is very classical, but I've given you a bunch of examples, and in every single examples above, you can see that there are a lot of natural group actions, or all the sets that we're looking at afford some natural actions, or it has some sort of symmetry. So for example, this thing, binomial coefficients, Sn naturally acts on the underlying set 1 through n. And here, the permutations are also acted upon by symmetric group Sn. And here, this one is also acted by Sn. And the graph matching numbers is counting graph matchings, but graph matchings are acted upon by the automorphism group of the graph. So for example, this one is D6, and it's or D12, depending on your convention. And it's like rotating the graph or flipping the graph, for example. So one can naturally ask, whether such log concavity behavior respects the underlying symmetry of the objects that we're counting. And how do we even think about such a problem? So here comes the notion of an equivariant log concavity to help us to think about such question. So, so you start with a graded finite dimensional representation, which I denote as V dot. That is the representation of a finite group H. And we say that such graded representation V is H equivariantly log concave if I look at every degree piece of this graded representation, there exists an H equivariant injection from the tensor product of the I-1 degree piece tensor with the I+1 degree piece into the ith degree piece and the tensor with the ith degree piece. So namely, I'm having sort of a vector space version of the definition of log concavity. So I want this to sit inside this other graded representation as an H sub-representation. So the second notion is slightly stronger. It's called the strongly H equivariant log concave, where I require for all k smaller or equal to L, there exists an H equivariant injection from the k-1 degree piece tensor with the L+1 degree piece into the tensor product of the kth degree piece with the Lth degree piece. So again, this is very similar to previous notion. So let me tell you a little bit about the strengths of such sort of group theoretic new notion of log concavity. So first of all, if you have an equivariant log concave representation of a finite group H, when you take the dimension of this graded representation, you automatically obtain the log concavity of the dimension sequence of this graded representation. So namely, if you have your favorite log concave concavity conjecture in your mind and you don't know how to prove it, one way to prove it now is if you can find some sort of graded representation that whose dimension is your favorite sequence that you want to prove to be log concave. And if you can prove that this representation is equivariantly log concave, then you win by just taking the dimensions. So this motivates the second point, which says some proofs are cleaner because now you can have representation theoretic approaches to prove this. And then the third thing is if you have two strongly equivariantly log concave representations, so are their tensor product. So this is something that's a little bit subtle when you were just looking at the sequences without looking at vector spaces. So in the case of sequences, it's not necessarily true that if you take their product, the resultant thing is also log concave. You have to think about something called internal zeros. And the fourth thing is that equivariant log concave is strictly stronger. So there exists representations whose dimension sequence is log concave, but the representation itself fails to be equivariant log concave. So here's an example. So if I just form a vector space or a graded representation that's given by just taking those partitions of 1 through n into k non-empty parts, and I take the span of all these partitions over your favorite field, and this vector space emits sort of a grading just given by the cardinality of the partitions, and this vector space also forms an SN action by just permuting the underlying partition. And notice that this representation affords an SN action, and the dimension of this representation is a log concave sequence. But in fact, this representation is not SN equivariantly log concave because my collaborator and myself have coded some program that showed that when n is equal to 7 and 8, and we look at say, the tensor product of the degree 2 piece and the degree 4 piece, and that does not inject SN equivariantly into the degree 3 piece tensor with degree 4 piece. Because we revealed that this tensor product contains one copy of sign representation as an SN representation, but this product does not contain our sign representation. So you cannot find such an injection. So, okay, so that is my pitch for equivariant log concavity, the notion thereof. So let me tell you briefly an example. So we have seen this claw-free graph example. So where you have G to be a claw-free graph, and you look at the sets of vertices that are non-adjacent to each other that have size K, and you collect those and span a vector space over your favorite field using those sets. And this naturally admits grading given by the size of these independent sets. So, and this automatically admits a action by the automorphism graph, of automorphism group of the graph. And one little theorem that I proved earlier this year, or the last year, was that this graded G representation is actually a strongly equivariantly log concave sequence. So now if you take the dimensions, you automatically recover the fact that the cardinalities of these independent sets of size K is log concave. So given the new proof of the result by Shadnovsky and Hamanui in the 70s, for example. So here, let me talk very briefly about the proof strategy. So the proof strategy is to first look at the definition. So what's our goal? So our goal is for each K and L positive numbers, we want to find injections from tensor products that are like this into the tensor products that are like this. So let's look at the relevant sets or relevant bases of these two vector spaces. So suppose my G is this 6 cycle graph, and suppose I take K equals to L equals to 2. And so this vector space will be spanned by pairs of independent sets that has cardinality 1 and cardinality 3. So those are the independent sets with exactly 1 vertex. And these are the independent sets on this graph with exactly 3 vertices. So namely, what I'm saying is now this graph has, say, 1 times 6 times 2. So there are 12 of these. So this one now is will pair itself with itself to give a basis for this vector space. So now we need to think about how do we send pairs of independent set of cardinality 1 and independent set of cardinality 3 into pairs of independent sets of cardinality 2 and cardinality 2. So here I have drawn like a picture of what we're trying to do. So it is a little unclear if you just sit down like me last year. And then, so here is one strategy. So namely, we want to create for every pair of independent set of size 1 and independent set of size 3, we want to create a pair or maybe a lot of pairs of independent sets of cardinality 2 and 2. So first what you do is you take a pair and you color the first independent set with blue color, and you color the second thing with red color or pink color, and you consider the vertex color subgraph that's induced by the symmetric difference. So by the symmetric difference is, I mean, you look at the vertices that are not appearing in, so that are not in the intersections, but appeared in either. So for example, in this pair, I obtained this as the symmetric difference, and I look at the induced subgraph. So for this pair, I look at the symmetric difference, and the induced subgraph will let me add these two edges. So you do so for all these pairs. And now we study the properties of these graphs. So you realize because the pairs you start with are independent sets, so you cannot have these triangles that have two vertices colored the same. And also because the graph you start with is claw-free, so the induced subgraph that you get at the end cannot have claws like this. So one major property that you get is that every component in this graph that's induced by the symmetric difference of these two pairs has to be either a path or a cycle of even size. Okay, so once you have done this, we want to do some combinatorics. So here is what we do this, how we do this. So you count the number of even length path components in this graph induced by the symmetric difference that has blue endpoints, so such as this path or this path. They all have even length. And we denote that number as B. And you do similar things for the path components with pink endpoints, and you denote that as P. And you also look at the total of these two numbers, and we denote that as E for even. And the second property that I want to deduce about this graph G is that the differences of these two paths exactly counts the discrepancies between the independent vertices that are colored red from the beginning and the independent vertices that are colored blue. Because the other components all have even size, so that you cannot have, so they contribute into the same number of blue vertices and the red vertices. So the only situation where you can have a component contributes into that discrepancy is coming from the components that we're looking at on this current page. So that means P minus B will have to be L plus 1 minus K minus 1, which gives us L minus K plus 2. But that number has to be greater or equal to 2. And now we just need to do some yoga to this inequality here. So B is equal to, of course, B plus B divided by 2. And that is less or equal to, now you replace this B with P minus 2 using property 1 here. And you also use the property that B plus P is equal to E. So in the end, you get that this count, which is the number of even length path components with blue endpoints, has to be less or equal to the total number of such paths that we are considering divided by 2. So that's an important thing because now we want to do is, so recall, we want to take a one independent set, size 1 independent set, and we want to take a size 3 independent set, and we want to create a size 2 and a size 2 independent set. So here's what we do. So for every single path component that has a pink endpoint, we'll swap the color. So for example, this one will become this one. So here, and then we do so for every single even length path component in the graph that's induced by the symmetric difference. So let's look at this example. So here I started with this pair, and the induced graph is like this. And for every component that's a path with pink endpoints, I'll swap the color as before, and I collect all the new vertices that are colored blue, and that will automatically give me a size 2 independent set, because after the swapping, I have increased that number by 1. So, and then in the end, for every pair, I will create a set of independent set of size K and paired with independent set of size L. So now to define this injection that was very important, I simply take every pair and send it, every pair or the pure tensor of every pair, and send it to the sum of pure tensors corresponding to the pairs that I have created in the previous graph, in the previous step. So the key insight up to this step is that I want to show that this map is injective. So conceptually, you can understand this graph as a raising operator on the Boolean lattice on all the even path components. So this Boolean lattice is ranked by the number of even components, even path components with blue endpoints. So this operator here is exactly going from this level, going from the B level to the B+1 level, where B is the number of path components with blue endpoints. And Stanley in 1913, actually way before that, but an easy reference is in this book in 2013. That says this map is automatically injective for the index that's below half of the rank of the Boolean lattice. So we have deduced before that the number this operator is going from the Bth level to the B+1 level, and here B is exactly playing the role of I. So you do some careful checking that your vector space is indeed isomorphic to, or can be decomposed into pieces that are isomorphic to such Boolean lattices. And then the operator on each pair is exactly this raising operator that we have described before. And then you say that, oh, because on each direct summand, the operator is like injective. So in total, we obtain a map that's injective on the total vector space or graded representation. So that concludes the statement or the proof of the statement that I've shown you. So a few highlights of known results is that this is actually a well-known, well-studied, but still just starting phenomenon that has a lot of geometric and topological interest. So for example, people like Mathern, Miata, Proudfoot, and Ramos have studied equivariant log-concavity behaviors for cohomology of certain configuration spaces. But there, it's not conclusive yet for all degrees. And for other combinatorial sequences, such as Q binomial coefficients, I think Proudfoot, Xu, and Yang in 2016 have proved that this Q binomial coefficients are equivariantly log-concave as well. And the result I have said before automatically gives as a corollary that graph matching sequences also can form representations that are Augy equivariantly log-concave. So that's a previous result of mine. And also as a corollary, you can show that this representation of Sn given by k subsets of 1 through n is also equivariantly log-concave. So I'll leave that as an exercise for you to think about how can you derive this thing using the main theorem of this talk. Like you need to find a graph claw-free such that the representation is isomorphic to this representation. So that's all I need to say. Thank you.